So intermolecular forces is the subtopic of this video. So our aims of this video are to know what van der Waals forces are, how they occur, and what makes them stronger or weaker, to know how permanent dipole-dipole forces exist and when you may spot them, and to know what hydrogen bonding is, know its importance, and be able to draw hydrogen bonding diagrams of it. So to explain how van der Waals forces arise, we need to look at a molecule of something. I'm going to choose nitrogen. Now nitrogen has 14 electrons. Nitrogen molecule has 14 electrons overall in the molecule, so 7 from each nitrogen. And we can think of these as being arranged around each nitrogen equally, so we can have 7 around one nitrogen, 2, 3, 4, 5, 6, 7, and 7 around the other, 1, 2, 3, 4, 5, 6, 7. Now what you must understand is that these electrons can move anywhere within the molecule once the molecule's been formed. And they'll do this at random and all the time. So the chance of there being an equal spread of electrons is almost zero, to be honest. And so at any one moment, the electrons could be on one side of one side of the molecule, or the other side of the molecule. So you may get a distribution that looks like this at one time, or you may get a distribution that looks like this in another molecule. Sorry, it's a different colour, you can't really see that. Looks like this in another molecule at another time. Now if this happens, or when this happens, there's going to be a dipole created. So what a dipole is a word to describe the fact that one end is going to be a certain pole, negative or positive, and the other end is going to be the other sort of pole, negative or positive. If there are lots of electrons on one side of the molecule, then that side is going to have a slightly negative charge, not a full negative charge, but slightly negative. And the letter we use to show slightly in this case is delta. So we write it like this. This side is going to be delta negative, and because the right-hand side of this molecule has less electrons than the other side, it is relatively slightly positive. This side is going to be delta positive. For the molecule underneath, that's going to have the dipole in the other direction. So the side with more electrons, the right-hand side, this time, is going to be delta negative, slightly negative, and the one with less electrons, left-hand side, is going to be delta positive. Now you can see there is going to be an attraction between these two molecules because this molecule has a delta positive and delta negative end, and this molecule has a delta negative and a delta positive end. So these two ends are going to attract each other, so you're going to find there are attractions between these two ends and these two ends. And those are what van der Waals forces are. Now they're very weak because as soon as these dipoles are created by the movement of electrons, they're destroyed again because the electrons are just going to move somewhere else. And so because they are instantaneous and don't last very long, the forces are very, very weak. There are two things that might make van der Waals forces stronger, which I'm going to explain to you now. And to do that, I just need to show you two different molecules. So we're going to stick with nitrogen for one of them, and we're going to think about fluorine for the other one. So nitrogen, sorry, just draw it. Nitrogen, as we stated before, has 14 electrons in its system. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And fluorine has 18 electrons in its system, 9 from each fluorine. So 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Fluorine is going to have much stronger van der Waals forces than nitrogen because of the number of electrons that are in the system. The reason why that's important is because if there are more electrons in the system, if there are more electrons in the molecule, that means that the dipole that can be created will be much stronger. So for nitrogen, the maximum difference in electrons that there could be is 14. There could be 14 on one side and 0 on the other. For fluorine, the highest difference there could be is 18. There could be 18 on one side and 0 on the other. So you can see that the dipole for fluorine, the maximum dipole, is much greater than for nitrogen. The other reason why more electrons can result in a stronger van der Waals force is because the chances of there being a dipole are much greater. If there are more electrons, then there is more likelihood of there being an imbalance in electrons across the molecule. The other factor that determines how strong van der Waals forces are is surface area. So you'll have come across this at GCSE. So if you took two alkanes, so here's one, I'm not going to draw the hydrogens in, I'll just leave them as sticks. So there's ethane, and we looked at butane. Because butane has a much larger surface area than ethane does, butane will have a much higher boiling point because it has stronger van der Waals forces, because it has a higher surface area for the van der Waals forces to act upon. You can think of it as a piece of Velcro. If you have a larger piece of Velcro stuck to each other, then it's going to be more difficult to rip apart than if you just had a tiny piece of Velcro stuck to each other. Now the upshot of this is that if you had to describe the difference between boiling points between two molecules that are held together by van der Waals forces, then you can use these two reasons to do that. So for example, if you had to describe the difference between boiling points of chlorine, bromine and iodine, then you can use these ideas, because these three molecules, the atoms are held together by covalent bonds, but the molecules are held together by van der Waals forces. Now you may remember from GCSE that chlorine is a gas, bromine is a liquid, and iodine is a solid, and so that means the boiling point must be increasing as you go down the group. It becomes much more difficult to boil them as you go down the group. You need a much higher temperature, so that means the van der Waals forces must be stronger. And the reason why they're stronger is first because there are more electrons in the molecule, so iodine has more electrons than bromine, and bromine has more electrons than chlorine, but also because their surface area is greater down the group. Iodine has many more shells of electrons, which makes it a much bigger molecule, and so if it's a bigger molecule, it's going to be able to create more van der Waals forces because of its larger surface area. Permanent dipole-dipole forces are similar to van der Waals forces, but the dipole that's created is not instantaneous, it's a permanent dipole, and this arises due to a difference in electronegativity of the two atoms that may be held together in the molecule. So if you just revise how electronegativity changes in a periodic table, the electronegativity increases as you go from left to right across the periodic table, or from the bottom to the top of the periodic table. So fluorine is the most electronegative atom, and theoretically francium, but we say that cesium is the least electronegative atom. Now if two atoms are joined together from opposite sides of the periodic table, so for example lithium and fluorine, their electronegativity difference is so great that the electrons spend all of their time on one of them. So if we had lithium and fluorine joined together, then fluorine is much more electronegative than lithium, so the electrons will spend all of their time at the fluorine and none of the time at the lithium, and this is what we call an ionic compound. So we'll have lithium plus and fluorine minus. Now that's not really what we're looking at when we say permanent dipole-dipole. That's something different altogether. So when we're talking about permanent dipole-dipole, we're talking about a bit smaller differences in electronegativity. So we're thinking about ones that are much closer together. So for example, if we joined carbon and fluorine together, their difference in electronegativity would mean that there wouldn't be, not all of the electrons would be at the fluorine, but a lot of them would. And so if we had carbon joined to fluorine, then again you'd have delta negative and delta positive, but that would be a permanent dipole. That would not change at all during the course of time. The same would happen if we had carbon joined to chlorine, and those are the two examples that you'd need to look out for in your exam. If carbon's attached to fluorine at any time, then you're going to get a permanent dipole-dipole. if you've got carbon attached to chlorine at any time, then you're going to get a permanent dipole-dipole as well. Generally, they don't ask you to spot permanent dipole-dipole forces in any other compound. You're always looking for carbon attached to fluorine or carbon attached to chlorine. You can follow that general rule in an exam. Now again, it's these slight charges on the molecules are what keep the molecules stuck together. So the positive charge is going to be attracted towards the negative charges, and the negative charges are going to be attracted towards the positive charges. And those are the forces that need breaking before your sample will melt or boil. Now, permanent dipole-dipole forces are stronger than van der Waals forces. So if you've got if you're comparing two molecules, so for example methane, CH4, and fluoromethane, CH3F, then fluoromethane has permanent dipole-dipole forces because the F is attached to a C, fluorine is attached to a carbon, so you get a permanent dipole-dipole. For methane, you've only got van der Waals forces, so that means that fluoromethane has a much higher boiling point than methane does because it has stronger forces within it. Now, hydrogen bonding is the third type of intermolecular force that you need to know about, and it only occurs when hydrogen is attached to one of three elements, either nitrogen, oxygen, or fluorine, and it's easy to remember those three because they're all next to each other in the periodic table. The reason why hydrogen bonding exists is because hydrogen only has one electron of its own. So if you have hydrogen attached to oxygen, for example, there is a big difference in electronegativity here. So the electrons are going to be pulled towards oxygen. Now, because oxygen already has its own electrons, it's also going to pull the electron away from the hydrogen as well. And what that will leave, if we look at hydrogen as an atom, if you take away its electron, then all you leave is a bare proton, and that is very attractive to negative charges. Now this positive charge doesn't attract to any old, well, it will attract to negative charges, but in compounds that have hydrogen bonding within them, this positive charge is attracted towards lone pairs on the other atom. So for example, in water, you've got lone pairs on oxygen. In ammonia, NH3, you've got one lone pair on nitrogen, and in HF, you've got three lone pairs around the fluorine. So the hydrogen is very attracted to these lone pairs because it's been essentially left as a bare proton as the electron has been pulled away from it, but the atom that's attached to hydrogen must have lone pairs itself to hydrogen bond with that hydrogen. So in an exam you may be asked to describe how hydrogen bonding comes about, and there are 3 points that you would make in order to answer this question. So the first point is the fact that there is a large difference in electronegativity between the hydrogen atom and the atom it's bonded to, either nitrogen, oxygen or fluorine. So large difference in electronegativity between the hydrogen and whatever it's attached to. The second point is that this large difference in electronegativity causes the hydrogen to become positively charged. So hydrogen becomes positively charged, and then finally you've got to say what that positive charge is then attracted towards, and it's attracted to a lone pair on another molecule. So H becomes attracted to lone pair on another molecule. And it's this attraction that we call the hydrogen bond. Another thing you may be asked to do is to draw a diagram of hydrogen bonding between two molecules that they've asked you to draw it between. I'm going to show you how to draw it between two molecules of water, but you may be asked to draw it between two molecules of ammonia or hydrofluoric acid, or any other compound, like for example ethanol, that has an OH bond. So there are 3 marks available for these sort of questions. The first mark, so always draw two molecules to draw the hydrogen bond between them. The first mark is we're drawing the dipoles. So hydrogen has a positive, delta positive dipole, and oxygen has delta negative, and do it for both molecules. Don't leave anything out, don't be lazy. The second mark is we're drawing all the lone pairs. Now remember, oxygen has 2 lone pairs, and you're going to draw them on both molecules. And the third mark is for drawing the attraction between the delta positive hydrogen and the lone pair on the other molecule, on the oxygen on the other molecule. Now, going back to the lone pairs, you need to make sure you draw all of them. So if you're drawing hydrogen bonding between 2 molecules that had nitrogen in, you just draw 1 lone pair on the nitrogen. If you're drawing hydrogen bonding between 2 molecules that had a fluorine in it, you'd have to draw 3 lone pairs on the fluorine, because that's how many lone pairs it has. So to summarise, you get 1 mark for drawing all the dipoles, all of them. You get 1 mark for drawing all the lone pairs, and you get 1 mark for drawing the attraction. And you must draw all the lone pairs and all the dipoles. That is very important. So as I alluded to previously in this video, hydrogen bonding is very important to the world around us, and this graph sums it up very well. So this graph shows us the boiling point of different molecules, different hydrides, that is hydrogen attached to another atom, for different groups in the periodic table. So the green line shows group 6, that's oxygen going to sulfur, going to selenium, going to tellurium. The blue line shows group 7, fluorine to chlorine to bromine to iodine. And the red line shows group 5, so that's nitrogen going to phosphorus, arsenic, antimony and bismuth. And the one I want to focus on is the green line really, although the trend is the same for each line. You can see that the boiling point of the first molecule is much, much higher than the next molecule down, and then it rises again. And the reason for that is that 3 molecules after the first one are all held together by van der Waals forces, and as you go down the group, van der Waals forces are going to increase because you have more electrons in the molecule and the surface area of the molecule is greater. If water or hydrogen fluoride or ammonia only had van der Waals forces, then their boiling point would be lower than H2S or HCl or pH3. And so if you think about water, if it was only held together by van der Waals forces, if we extrapolate the green line, then water would have a boiling point of about -80, which would mean that water would be a gas on Earth if hydrogen bonding did not exist. Now that has obvious implications. If there's no water on Earth, then life couldn't exist. Hydrogen bonding also has importance in DNA, so hydrogen bonding is very important in holding our DNA together, and proteins as well, which you could ask your biology teachers about. And it's also important because hydrogen bonding is the reason that ice floats, which I'm going to try and describe in the next slide. So to try to describe what hydrogen bonding has to do with ice floating, first we've got to look at what happens normally to liquids when they turn to solids. So we're going to go back to our Year 7 particle diagrams. So for a liquid, all the particles have slight gaps between them. They're all joined, but they can flow over each other because they've got gaps between them. When they turn into a solid, when they freeze, all the particles then become a rigid structure with no gaps in between, and they can't move over each other. That affects their density. If the particles are much closer to each other, as they are in a solid, that means they're going to be more dense. And so usually solids of the same element or the same substance do not float in the liquid because the solid is more dense. If, however, we talk about water, when water freezes, so first we have particles that can move over each other. When water freezes, hydrogen bonds are formed, and hydrogen bonds create a more rigid structure than the liquid had before. So when water freezes, what we have is that the solid particles are more like they're a structure, but they have gaps in between the particles due to the hydrogen bonds pushing the molecules away from each other to form this structure. Now that means that the solid water has a lower density than the liquid water, and so it will float on top. Now again, if ice didn't float, then marine life couldn't exist because the bottom of the ocean would be frozen and the top would be, the liquid would be lying on top of it. And so you can see that hydrogen bonding is very important in the way that life exists on Earth.